but today we're going to talk about a special kind of sound. Ultrasound. Amazing.
Doctor, my morning sickness, it's gotten worse.
You sound like you need an ultrasound. I'm here with a real-life expert. Earth Tim is going to explain to our patient how an ultrasound scan works.
Thank you, Professor.
Amazing.
Welcome, Ben. With baby on the way, it's about time you learnt about ultrasound. Here we have an A scan I made earlier. An A scan, or amplitude scan, sends waves of ultrasound into the body and measures the time at which they take to reflect back. And this is shown by this graph here, where we have time along the x-axis and the amplitude of the reflected signal on the y-axis. And the distance between these pulses that travel through the body and come back to the transducer can be used to work out the distance between these points. And this can be used to precisely measure the anatomy of the body.
We're at the 18-week mark now. That means it's time to see how Tim and Ben are getting on. Today we're going to do a B scan. B for brilliantly amazing.
Thank you, Professor. All ready, Ben? Just before we start the ultrasound, we need to put on some contact gel.
What's that?
I'm glad you asked. We need to use a contact gel because of a property of materials called impedance. Air and skin have very different impedances, which means if we send the sound waves through air, then nearly all of the sound waves are going to be reflected off his skin. Amazing. But if we use a contact gel, which has an impedance very similar to skin, it means that very few of the sound waves are going to be reflected off the skin. Amazing. In order to properly understand impedance, we need to talk to a mathematician. Amazing. Hi there. You just caught me doing some maths. So, we give impedance the symbol Z, and we define this as the speed of light in the medium times by rho, the density of the medium. And then we have an equation where we can work out the ratio of the reflected intensity to the transmitted intensity. And to do this, we find the difference between the impedances, square it, and divide it by the sum of the two impedances, and square it. And now, if we look at the impedance of air, we get a value of about 1.6 times 10 to the 6. But the impedance of skin is very different, of only 440. That means when we plug this into the equation, we get a value of about 0.99, which means that nearly all of the reflected intensity, nearly all of the original intensity is reflected, and so we get very little sound waves going through. However, if we use a contact gel, which has a Z value very similar to that of the skin, then we'll have much less of the original intensity being reflected, and so we'll get much more sound waves in our scan. Amazing.
Hello, Ben. Now that baby's getting bigger, it's about time you had a B scan, or a brightness scan. This ultrasound method uses many transducers to combine multiple A scans to give a 3D or 2D real-time image of what's inside. The amplitude of the reflected signals from the transducers dictates the brightness on the display. And as different tissues such as bone, liquids and muscle tissue reflect different proportions of the ultrasound, this affects the brightness on the display. This is commonly used to check for abnormalities in babies. I've got some bad news, Ben. Your baby's going to be ginger.
They ask you how you are, you just have to say that you're fine when you're not really fine, but you just can't get into it because they would never understand.
Ben is expecting any day now, so I've come to visit him in the hospital.
Doctor,
Amazing.
my waters are breaking.
Don't worry, Ben. We'll do this. Oh, you've given birth to a beautiful baby clown.
Now, I'm here to talk to you about something amazing. Something we use not only in our ultrasounds, but also to date the age of the universe. I'm here to talk to you about Doppler scanning. Amazing. I'm here with a real-life expert who's going to give us a visual demonstration of the Doppler effect.
That's right. I'm Professor Devin, and today I'm going to show you a demonstration of the Doppler effect in action. This is kind of the further maths way to do it, but I'll show you anyway. So here we have a normal wave, quite a normal wave. Now I'm going to have my associate move the whiteboard, and this is going to be similar to moving the source. Okay, so here we go. That much higher frequency here, and this is because the source was moving towards the wave.
Amazing.
Amazing.
I'm here with Dr. Tim, who's now going to examine another patient who is believed to have an aneurysm.
Let's have a look at the patient. Hello, Rick. Are you ready for your checkup with your ultrasound?
Ultrasound? That sounds like some kind of 90s rock band.
Well, here are some advantages I prepared earlier. Ultrasound is non-invasive. I don't have to cut your neck open to have a look. And it is real time. We can analyse how the blood is travelling in your body to work out where your aneurysm is. It is also non-ionising. Some techniques would cause mutation in the cell, but this one is very safe.
That's alright.
I have some bad news. Rick's aneurysm has gotten worse. So we need to give him an urgent ultrasound. So we place the transducer on his neck after putting on some contact gel. Notice the angle here. It's about 30 degrees. And we can use the Doppler scanning to analyse the blood flow in his neck and identify the clot. And hopefully save Rick.
Why do we have it at an angle of 30 degrees though? In order to understand that, we're going to have to talk to a real-life mathematician. Amazing. Now, hello there. I was just doing some surface integrals. It's quite simple really. But so, this is a diagram of an ultrasound transducer. As you can see, we have the blood vessels here with the blood flowing in this direction. And we have the transducer at an angle theta. Now, the change in frequency obeys the equation 2v cos theta. And we want to maximise this so we can get the clearest signal out of our ultrasound. And the way we do this is we want to reduce the angle theta, because when this is between 0 and 90, the smaller the angle theta, then the bigger this will be. Ideally, we'd have this be 0 degrees. So we'd have cos of 0 is 1. But obviously we can't put this at the same angle as the blood vessels, because this is inside their body, and that would not be good for their general constitution. So in practice we use an angle of theta about 30, which, as we all know, cos 30 is root 3 over 2. Thank you very much. Okay guys, we are going undercover in the hospital. Let's catch up on Rick.
Ah, hello, Professor.
Excuse me, can we just catch up on how Rick's doing?
Oh, no, there's no need for that. He is doing
no.
very well. Honestly, no, Yes, the patient is dead, but it's important to remember that ultrasound didn't kill him for these reasons.
Now, Professor Rick is going to demonstrate the Doppler effect in real life. Amazing.
The Doppler effect is the apparent change in frequency due to a moving source or object. For example, as Rick's motorbike moves closer to the observer, the observer would hear a higher pitch or frequency. As it begins to move away, the observed pitch would be lower. So, anything more you want to?
Amazing! That's horrendous. Amazing! Amazing! Amazing!
How an ultrasound scan works.
Amazing.
You see, the skin and the... Wait, no.
When you are. Yeah. So if I do it, keep going. If you can jump a good distance sideways, we're all right.
I'm here with a real-life expert who's going to give a visual demonstration of the Doppler effect.
That's right.
Okay, no.
Let me finish my licorice. Have a tea, please, Mum. Hi there.
Get out of the gaming room.
Amazing! You got this.
3, 2, 1.
Stop! You're ruining our film.
You're ruining our documentary. Yep.
The nose was fine.